So this subunit is called Some Application of Vectors. It's really brief and it just gives you a general understanding of where would we use vectors. We've gone through all the ways that you can manipulate them, but where do we actually use it? One key way to use a vector is in this physics concept known as equilibrium. Equilibrium is just a fancy word for saying balance, okay? When two things are in balance, or when something is, let me try to balance this. Hold on. All right. When something is balanced, we say that it's in equilibrium. But it's not as simple as just making sure the thing isn't moving. Something in motion can also be in equilibrium. Now, the physics definition of equilibrium is the resultant of the vectors acting on a body is 0 Newton. See, now we're using vector terms in order to describe equilibrium. We know what a resultant is. We know how to find the resultant if the vectors are parallel, if the vectors are perpendicular, even if they're not parallel and not perpendicular. If you don't know what I'm talking about, you might want to look at the previous subunit on the addition and subtraction of vectors. So, we know that we can find the resultant of any vectors acting on a body. Okay, if we find the resultant, and the resultant is 0 Newton, this could happen. You could have vectors in all sorts of directions, and when you add them up together, they turn out to be 0 Newton. This body is in equilibrium. Right, now, if you want to prove an equilibrium graphically, we use something called the triangle of vectors, okay? Let's say we have three vectors. Let's say one is going this way, vector A, and one is going this way, vector B, and the final one is going this way, vector C. So this is what I mean. These vectors are going in crazy different directions. But I can prove to you that if all these vectors act on one point on one body, the resultant will be 0, or the body will be in equilibrium. How do I do this? Well, let's draw the vectors separately. Let's draw the vectors again, but this time, let's graphically draw them in a head-to-tail position, okay? Remember, we did this when we tried to solve perpendicular vectors, and it really helps graphically to solve a lot of problems concerning vectors. So let's start with vector A. So I have vector A here, right? I'm trying to draw this as similarly as possible. Now, vector B, use the head-to-tail relationship. So the tail of A, no, the head of A, I'm sorry. So the head of A just means where the arrowhead is. So the head of A will be connected to the tail of B. I'm drawing them in the same direction, technically, in the same angle as what they were before. I'm just moving them or transposing them into this new location. And finally, for C, we connect the head of B to the tail of C. There you go. What have I formed? A triangle. Yay! So what this triangle proves is these three vectors. You see how they connect. The head, tail of each vectors all connect until it comes right back around to the initial point. This means that this body's in equilibrium. Because if I were to mathematically, we'll see this in a bit, but if I were to mathematically add these three vectors, I would get 0 Newton. But graphically, you can see that if I were to position these vectors head to tail from each other, without changing the direction, it would come right back to where it started, which is how you graphically prove equilibrium. Next, how do you mathematically prove equilibrium? Well, what you do is find the summation of vectors in the x and y direction. So you'll remember that when we resolve vectors, okay, we split the components, then we add the components in the same direction, right? So right at that step, if we add the components in the same direction, so if we add all the y's together, and if we added all the x's together, and the resultants became 0, that is equilibrium, okay? We don't even have to go to the step of solving the two perpendicular vectors, okay? If we get to that point where we add all components in the x direction and add all components in the y direction separately, we'll get 0, 0 for both. And that will form, that's how we mathematically prove, what you call them. That's how we mathematically prove if a component is in equilibrium. Okay, that's the end. So, alright, so if I were to draw this again, it should be with numbers, but if I were to draw this again, let's say we have our three vectors, okay? Let's see if I remember how I drew them. We have our three vectors, A, B, and C. Okay, so let me just roughly draw what I believe the components would be. So for vector A, I'd say that the AX component would be like this, and the AY component would be like this. Okay, for B, I would put it in the other direction. This would be our BX component, and this would be the BY component. And for C, this would be the CX component, and this would be the cy component. You see how even though the vectors are pointed in a whole bunch of different directions, I can always find the x and y components. All you have to do is the steps that I mentioned in the previous video. You should probably check that out. All right, now, you should probably check that out if you don't know what I'm talking about here. Now, what is the next step? Put all similar components together, right? So, if I were to draw ax, if I were to add ax, bx, and cx, and if I were to add ay, by, and cy, and if these three vectors acting on a body were in equilibrium, then I already know what the resultant is going to be. I already know what the answer is going to be. When I add all the x components, the answer is going to be 0. And when I add all the y components, the answer is going to be 0. Let's say 0 Newton, because I'm applying a force. I'm applying 3 forces onto this body. So that is how you mathematically prove that vectors acting on a body make that body in equilibrium. That's it for the first unit of grade 9 physics. This unit, vectors, is very, very, very important to a lot of upcoming units. If you don't understand this unit, look back, revise on some of the units, do questions, and we'll do some sample questions too on upcoming videos. Stay tuned for the second unit of grade 9 physics. Thanks for watching.